Here I am back in my garage after a fantastic MomoCon 2023. This convention gave me my first opportunity at hosting a solo panel where I talked about bringing high tech to cosplay. And in this panel, as you'll see, I cover everything from, how to get started with wiring and electronics to begin with, all the way to how to bring advanced electronics and computers like Jetson to your cosplay projects. I'm not going to spoil anything. We're just going to jump right into the panel. First of all, I do want to thank everyone that attended the panel. You were a fantastic audience, and I couldn't have asked for a better first experience. So thank you all who attended, and I will see you at the end of this panel for a few brief comments. Okay, we're going to get started. Like I said, I'm going to try to project because it's just easier on me, but if anyone can't hear me, I'll be happy to pick up the mic. It's not a big deal. So what are you here for, and what am I going to be covering? So obviously I was given no script and just decided to share what I know and hopefully get some of you to the next step. So the question is, of course, where are you? I think everyone's probably at a different point in this journey. You've either tried to put LEDs in your cosplay and it's gone horribly wrong and it caught fire, or you're to the point where you've got an Arduino board and you're trying to learn how to code and that's kind of working, but it doesn't always last very long. So all these different levels of cosplay and what you can do with technology. And so I'm going to try to walk you through the very beginning to where I am, and so everyone will kind of be able to pick it up where they are. Obviously, we've only got an hour in here, so I can't delve real deep into any one subject, but I am going to try to leave plenty of time for questions. So if you have specific questions about the voltage of an LED or how do you wire this thing up, I'll do my best, or you can see me afterwards and I'll hang out outside while people are trying to get in here for the next panel. All right, so who am I? So I am Kris Kersey. I have been cosplaying, I guess, half my life at this point. I make everything from props out of wood and make bows, and I sew, and I didn't make all of this, but that's me in the arrow costume. Here's me with my kids. I've been actually spending probably more time making kids' costumes for the past 10 years than I've been making costumes for myself. So these are my daughters. I made the cloak here on the left. Most of the X23 was store-bought except for the claws. Here's me in a couple of other costumes. I also do productions with my children, which is what I've got on the left, and on the right is the Georgia Renaissance Festival. Yeah. All right, this is me last Dragon Con with a bunch of my fellow Iron Men. They're all the ones in the fully completed suits. I'm the one that I'm still working on the tech, so I haven't finished the whole suit. So what you're going to see in this presentation is the tech that I've got in there. I went for the prototype Iron Man 1 look, but plus a helmet. All right, I'm also big into 3D printing. So I have a YouTube channel with just over 35,000 subscribers that has primarily been focused on 3D printing technology, 3D printer reviews, modding 3D printers, that kind of thing. So here you see me printing a lot of what you have up here on the table. On the left is the helmet itself. On the right is a motorization system that isn't quite in here yet because I ran out of room in the helmet. All right, I also do some 3D modeling. I'm very good at mechanical design, not very good at the artistic design, so you won't see me designing the outer shell for the costume, but you will see me designing anything I can do geometrically. I'm pretty good at. So what you see here on the left is the arc reactor, which I have here on the table, and inside of here is a miniature computer, which you can kind of see there on the graphic on the left. I designed all of that. And then what you have here on the right is what is inside the helmet, which is the heads-up display. All right, this is my YouTube channel, and I've got a clip of the video that basically describes what I built here, just to give you a little teaser of what you can find on my channel and what I'm working on. I don't know if I have audio. I'm actually not expecting audio. So if the audio doesn't work, I will verbally walk you through what we're going to see here. Well, as you can hear, it is playing off of my laptop. So here's the Iron Man helmet with the arc reactor. And here you're going to see a little clip of what it looks like inside. That is what I see inside of the helmet when I'm walking around. And this is near real time. The delay from camera to Actually seeing it is about 80 milliseconds. There's a cool logo that my friend made for me for this video. This is how I get started when I'm building something. It is on a table with a 3D printed board and the hardware all connected to it. So this is where you start and this is where you finish when working on a project like this. I find that having everything laid out for me makes this a lot easier to work with than trying to work with it when it's kind of in its final form here. This is an NVIDIA Jetson board, which is basically a kind of like your cell phone plus an NVIDIA graphics chip. And that's what's powering this helmet. That's the camera that is in both of the eyes up here. I do have stereo vision, so it is full 3D. I have depth perception and everything inside of the helmet. And that's what it looks like just when I'm doing some demo work. I'm learning, so it has object detection on here. And this is me soldering up. So in the top of this helmet is actually another computer that handles all of the processing of the inputs. So the green board there is the little computer. I've got a 9 DOF sensor, which basically does the roll tilt sensing of my movement. I've also got a temperature sensor, and I've also got a GPS. So you will see a mini map on here, as people like to call it. And so it actually does pull down live maps from Google Maps. That's the displays inside, 120 hertz refresh rate, 2K displays. That's me printing the helmet on a large printer. This is me making it all fit for the first time, which is you take a faceplate, you Dremel it out, you get it fitting until you can put the displays and everything inside. Inside, I'm a big fan of these little melt-in inserts that makes it where you can adjust. That's all the errors during the process. And this is the graphics display and everything that is inside the faceplate. It's all connected to one unit that I can pull out and work on. I'm a big fan of modularity because if it's modular, then you can take it out and work on it. This is me taking it outside for the first time and deciding to actually walk around and try it out in a public place. So I went to Suwanee, Georgia. They have a very nice town center there. And I decided that I was going to put all of this on and walk around and see who I ran into. And if anyone's ever cosplayed in public, it is fantastic. Oh, yeah. People love it. Like, every now and then you'll get the one person that tries to say something snarky to you, but overall I find kids love it. A lot of, decent human being adults love it, and it's been very positive to me anytime I've done it. So this is me. I've got this little separate display where I can show other people what I'm seeing. It does a live stream to that display from the helmet. And this is what I see. And as you see here, I run into some kids, and they like I said, they absolutely loved it. Ran into Spider-Man here, which I just thought was fantastic. There's my Peter Parker moment. And as you can see, this is all the object detection. I'm actually doing live, real-time object detection of all the human beings in the frame. It also detects cars and dogs and other stuff. I'm actually using a generic data set that is available from NVIDIA. And so I didn't have to program I had to do all the programming, but I didn't have to do the object detection algorithms. That's something that NVIDIA provided. I have this wireless Bluetooth keyboard that allows me to turn on and off different features of the heads-up display. So, if I get tired of looking at something, I can just turn off this section and give myself more visibility. This is something that later I can tie into something like voice controls. So, Jarvis in the future. I'm going to go ahead and go to the next one. So before we get there, we have to get started. And I'm going to again, this is very generic. If I say something that you think is wrong, I apologize, but I am trying to cover this in a very basic sense. I'm also trying to appeal to the largest number of people. So what I'm trying to describe here is how it kind of works so that people can understand it. So when dealing with electricity, and I do want to cover this because unless you can put a wire to an LED and then back to a battery, you really can't get started. So that's why I'm covering something so basic. So when dealing with the circuit, you have voltage, current, and resistance. You may have heard of an equation, V equals IR. It's the most basic equation in all of electricity and circuits. And basically, you need to know these three things. Basically, resistance is what gets in the way of your circuit and basically limits certain parts of the circuit. Voltage probably is the most important thing anyone in this room really needs to know about. If you put too much voltage into something, that's when it pops. All right? So anytime you buy a circuit, almost everything is going to have a voltage on it. So if you buy an LED, make sure it says this is a 3.3 volt LED or this is a 5 volt LED or 12 volt LED, because that immediately tells you what kind of battery you need to hook up to the circuit. And if you buy a LED that is less than what you plan on putting into it, that's when you need resistance to slow that down. I'm going to let you guys research how to figure out that math there, because that's a little bit more than we want to do on a whiteboard up here today. But so voltage, pay attention to your voltage. If it's a 5 volt component, don't put 12 volts into it. It will go pop. If you put 5 volts into a 3.3 volt component, it may not go pop immediately, but it will probably eventually go pop. Current. So what you need to know about current is basically there's a certain amount of current your battery is going to provide. Right? And when you run out of that current, then things start to brown out or there's not enough power to keep them going. So again, a little bit more than we can talk about here, but current is secondary. Most everything you build will have enough current to power it for a certain amount of time, and then it runs out, and that's when you're out. So current, when I'm talking about, you'll hear something like milliamp hours. That's what we're talking about. And the milliamp hours, it says it can provide this many milliamps for this number of hours. So something like an LED could be powered for days off of a small 5 volt power supply, right? But something like this computer needs this thing to run it for an hour and a half. Oh, wow. So again, that's the differences. And I do want to cover real quick, I didn't put it in the presentation, but the idea of like, what do you need to power a circuit? So if you're just powering a few LEDs, you're talking about usually a couple of AA batteries will be fine. You can buy little battery attachments that you put the batteries in and solder it together. That's all you'll need for a couple of LEDs. When you start dealing with little mini computers, or if you start dealing with other things that need more power, you probably start looking at these fantastic little 5 volt power banks. I use these all the time. These are fantastic. They will power most circuits for hours and hours and hours. Okay, and you get these on Amazon. And basically what I start looking at is how big of a spot do I have to put it in the cost to you? Right? These come in all shapes and sizes. They come smaller than this, thinner than this. Like I said, this big, which are laptop power supplies, right? And like I said, these which have USB ports are almost always 5 volts, because that's what USB is. USB is 5 volts. Okay? When you start talking about circuits, if you're taking notes, your common voltages are 3.3, 5 volt, 12 volt. Occasionally you'll see 24, but not as often. Okay? I think 12 volt is common for automotive. 5 volt is common for USB. You had a question?
Yes. So when you're thinking about powering the whole system together, I suppose, do you like to do that all on one power source, or do you integrate different power sources throughout it?
To me, it's a couple of things that I think of. Number one, if you have something that's going to use a lot of juice and a bunch of things that aren't, you may want to put all those other things on one power supply and the thing that's going to suck up more on a second. That's one consideration. The other consideration, like what I'm doing in the Iron Man suit that I'm working on, is so when you start wiring up a complete suit or even a large cosplay, you may want to start thinking about how's your wiring going to look. If you're running wires down your arms and down your legs and trying to reach all one power supply, all of a sudden, now you have a wiring just disaster waiting to happen. Either you're going to catch it on something while you're trying to put it on, it's going to come unhooked, you're going to break a wire because they are so long. So I also think of it in terms of compartmentalization. So like in an Iron Man suit, I find that like you could power the chest, and then you could power each gauntlet. But I know plenty of Iron Man cosplayers that will run wires through their whole suit and have quick connects in different places. So it's up to you. It's also a weight consideration, because these are the heaviest thing that's probably going to be in your suit or in your cosplay of any sort. So keep that in mind. Weight, wire lengths, and just power consumption. Basic circuit, I just wanted to show you one if you've never seen one. So we have basic circuits, and again, we've got 5-volt batteries and 3-volt batteries and 12-volt batteries here. And this is a basic circuit. It is a power source. It is potentially a resistor, particularly if the thing you're powering doesn't need as much juice as you're giving it, right? And then something you're powering, such as an LED. And to complete a circuit, yes, it has to go back to the battery. If you're not aware how circuits work, electricity moves. Not technically, there's a YouTube video on that, but electricity moves around the circuit and you do have to complete the circuit. All right, we also have things like motors. Motors suck up a lot more juice than LEDs do, but the circuit wiring is pretty much the same thing. And you can, of course, add switches wherever you want to. Switches are fantastic because it allows you to keep things connected and flip a switch when you want to cut it on and off. I do recommend switches in almost every circuit because it gives you a quick way to turn things on and off without breaking your circuit potentially, right? It's one less thing that while pulling things apart, you pull out a wire, and that happens all the time. And you don't have your soldering iron with you, or you don't have extra wires with you, and you can't fix it. And I bet you the cosplay people don't always have, the cosplay repair shop doesn't always have a soldering iron. One other thing I want to mention here, if you are doing two things that need the same amount of voltage, you have to wire them in what's called parallel. You cannot wire them in series. Okay? Parallel means that both things need to go to the battery, right? You cannot wire one motor and then into the next motor and then back to the battery, because what you've done is split the voltage between them. They will be underpowered. So if you have a bunch of LEDs, those all need to be wired in parallel. Soldering, I did want to cover it real quick. Obviously, this is not a soldering class, and that's a whole different thing because I hate soldering as much as the next person. I will give you a quick tip. My favorite temperature to run a soldering iron is 325 to 350, somewhere in that range, depending on what I'm soldering. More if you need it, less if you don't. Always start low and work your way up. All right? And this is something I found from Adafruit I thought was really nice. It's just a very basic diagram. I looked up soldering, or beginning soldering, or soldering 101 on Google image search. This is what came up. This is a really just good primer on how to solder. When dealing with anything beyond, okay, so at this point I'm done with the basics. Now we've built a circuit, we've made LEDs, we've put on some motors. These are things that don't need smarts, right? LEDs just turn on and off if you don't have a computer attached to them. Motors just turn on and off if you don't have a computer attached to them. They work really well, right? But the second you want an LED to start blinking, you're going to need some sort of smarts to it. If you want circuits that do things in series and have a pattern to them, you're going to need smarts to them. If you want things like servos, although I've known a few people that have figured out how to hook up servos without a computer, that's up to you. Go check out a channel called Frankly Built. Frankly Built knows how to do it. But I've never even tried to hook up a servo without a computer. But I wanted to talk about these ready-made kits by companies like Crashworks. They're fantastic. They've already written a bunch of code for you. You see they already have these fantastic quick connects already so that you just plug in your components. Crashworks specifically works for cosplaying. They're targeted at Ironmen, but they also do a few other cosplays that they've been contracted to help out with, and so they have some other code from some other cosplays. If we've got a few minutes afterwards, I do have one of these Crashwork kits hooked up here on the table. And again, this is your servos already connected to it, your switch is already connected to it, your LEDs for your eyes is already connected to it. The code comes already on it. So literally you plug this into a 5-volt battery source and you hit the button, the servos run, the lights cut on, and you've got a wired up Iron Man helmet. All right? So these guys are fantastic. If I'm not mistaken, and don't quote me on this, I think these kits are about $50. They come with the microcontroller, which is the board in the middle. They come with the red board, which comes with everything you attach it to. And they come with all of the wires that you need to hook up to your other components. So you have to do just a little bit of soldering to connect it to your own components and stuff, like the eyes and stuff, which you can buy any numbers of places. But It's about 50 bucks and you're ready to wire up your Iron Man helmet. Right, and this is basically what they've done for you. All right, so again, they have the microcontroller. They've got a button. You plug it into your 5-volt battery source of whichever type you want to hook it up to. You've got a couple servos and a couple of LED lights for your eyes. And then you have these fantastic kits, which you can find on Amazon all day long or any number of other sites. I promote Amazon because I like things tomorrow. So right here, these are fantastic ways to learn. Okay, you buy a whole kit, and you see this one right here is $33. And it comes with everything you see over there. It comes with boards and breadboards and LEDs and motors, and it comes with all your wiring diagrams. It comes with all the code to get started so that you can learn how they work, right? And so you go through all of their examples. You start learning kind of how to look at code because they've given you examples, and you kind of step through it and learn how it works. And this is a fantastic way to get started. Now, if one of their sample codes does what you want it to do, you're done, right? You wire it up, you run wires long enough to do what you need to in your costume, and you're good to go. Or if you just learn, hey, I want to do this and this. Well, now I'm going to learn a little bit about how to code. I'm going to take this program and this program. I'm going to mash them together and figure out how to do it. Everything I can't teach you in this is available online. And that's one of the things I want you to leave here today is where can you learn what we don't have in an hour to teach in this class, right? Adafruit is absolutely one of my favorite places. I go to Adafruit, I buy from Adafruit, and I will tell you right now, Adafruit is not one of the cheapest places you can buy from. But what you're doing when you're buying from them is you're supporting all of the learning and all of the code and all of the libraries and everything that they do at Adafruit. So take that for what you will. Very often I will buy my first one at Adafruit, and then I'll go buy the other one somewhere else if I need a whole bunch of them. So just keep that in mind. And when you buy from them, it is an American company. They make everything in New York, so everything is local. If you have support issues, they're available. There are forums. You're working with people that are running on the United States time, and so it's a little bit easier to get support from them. And so I support them. Another local company, Sparkfun, fantastic company. It's a company very similar to Adafruit in terms of what they make and what they provide. I think I find Adafruit stuff a little easier to follow. I think Sparkfun's is probably a little bit more advanced. So take that for what it's will. Go check out both of their websites before you buy anything. You go see one of their products. You find something that looks like it does what you want it to. Then follow the learning stuff before you ever order it, right? Because all of this you can download, you can compile, you can get it working in the development environment before you ever order the part. And then you order the part and see if it does what it's supposed to. But give it a shot. Give it a shot ahead of time. Again, Adafruit.com, Sparkfun.com. Go check both of them out. Lots of learning stuff on their website. And so, Adafruit also has a lot of projects. So if you're not sure what you want to make with electronics, but you want to learn, they've got these great kits that you can buy. They also have a box that they put out every few months where they send you a whole bunch of stuff in one box with the kits, with the code, and it's also a really good way to learn. I actually subscribe to the box because I get a whole bunch of components at once, and it's a lot of fun to play with. Languages. So again, we're stepping it up here. I'm going to talk about the next level, and so the next thing you're going to care about is which language am I coding in, right? Well, two of the most common languages you're going to find is C and Circuit Python. Is there one better? Not really for what we're doing, right? I'm an old school C guy. I've been a software developer for over 20 years. I've always done C. I'm an embedded software developer. But Circuit Python's come around, and it's a lot easier for some people to get started. I don't have a preference, whichever one you want to try. If you want to take a look at both code, if you go to the Adafruit website, almost everything they sell, if you're going through the how-to guides, right? Almost everything they sell actually has C code and Circuit Python code. So if you want to know how do I compare these two? How do I go look at both of them, read the code, see does one of these make any more sense to me than the other. I think Circuit Python might be a lot easier for some beginners. I know a lot of people tout Python as a good beginner code base. It also is really nice. You plug in the device and kind of drag and drop your code to it, and that's how Circuit Python works. But anyway, you got two choices here. There are references for all of this online, though. So don't worry about it. Like, if you're learning either one, there's plenty of support in both communities to help you out. Okay, so what's beyond this level? So once you've learned some Arduino, once you've learned some Circuit Python, once you've ordered a lot of different things from different companies, you're starting to get going. You can do almost anything in Cosplay you need to with that. Like, that's where you're at. You can buy sensors that do motion sensing, like I've got here in the helmet. You can do sensors that do temperature and humidity sensing. You can do sensors that, again, they've got controllers for servos and for motors and all sorts of stuff, right? At that point that you can do Arduino, you've pretty much got everything that you need, okay? That just becomes a complexity of code at that point. So you can make your code really simple, you can make it complex, you can make things do really, you know, how much animation do you want to your cosplay, or how many buttons do you want on your cosplay to do something? But at the point you want to build a Halo costume and you want a pad on your arm that actually controls things, Arduino's now probably not going to do what you want. And again, I'm speaking generally here. Okay? If you want to build an Iron Man heads-up display, I promise you Arduino's not going to do what you want. All right? And so you have even more levels here. So Raspberry Pi, most people have heard of Raspberry Pis at this point. Raspberry Pi is a fantastic little ARM-based, and ARM is the microprocessor, ARM-based mini computer. Okay, it runs Linux operating system most of the time, and you can, anything you can code on a computer, you can run on Raspberry Pi for the most part. Right? Limited processing capability, limited graphics capability, but it will do almost anything you want. That, I mean, people use Raspberry Pis as desktops, so they do almost everything. Yes?
Would you recommend like a Raspberry Pi, Jetson, or like an Arduino for splitting display output from one sensor to binocular vision, like a heads-up display?
So if you wanted to do something small scale and very specific, an Arduino will do it. You'll need to do a little bit of research. There are some microcontrollers that have more power than others. I'm a big fan of the Teensy microprocessors. They're very powerful, have a lot of inputs and outputs. But if it's just doing one thing, like one sensor input, one screen output, something like that, that's how I started experimenting with thermal sensors. And so similar to what you're talking about, I literally have an Arduino-based computer, and yeah, that little thermal sensor on one side and a little screen on the other side. If you start doing any sort of processing with it, though, overlays, okay, as long as it's just straight out, you probably can do it with Arduino. You get a couple and you experiment with it, and performance is ultimately going to be like, it's too slow, I'm not happy with it, it's not running fast enough. That's where you start deciding whether you want to upgrade to something new. Okay. Obviously, when you start stepping up to Raspberry Pi, one of your biggest problems is it uses more power, it takes up more space, it requires more code. It's a PC now, right? So treat it like a PC and you'll understand what I'm talking about, right? You can write C code and Python code on a Raspberry Pi. So once you've learned that on the Arduino, it's a transferable skill, right? It might be a little bit different. The code might be a little bit different because you're on a different platform, but it's pretty much a transferable skill at that point. Yeah.
Can you mix like breakout and daughter boards from Arduino with the Raspberry Pi and Jetson and stuff?
Yeah. So almost every one of the little microcontroller boards, whether it's Jetson or Raspberry Pi or whatever, they have a very similar set of GPIO pins, what they're called. And those pins can be used for things like I2C, which is a type of data bus, SPI or SPI, which is a type of data bus, or what's called GPIO, which is just general purpose input-output. Now, the only thing you have to worry about is a lot of times is while there might be these wonderful Arduino libraries that make life easy for you, there might not be a library to support every one of these things on Raspberry Pi or Jetson. Okay, so for example, these LEDs on top of this arc reactor here, those are actually controlled by the computer. There's actually this breathing that's going on that's very subtle on there, and that is being controlled by the computer itself. Okay, and so that is hooked up to the SPI pins on the Jetson, and I've got a little Python program running in the background that's doing that. And I had to find a Python library that knew how to do that. Otherwise, I would have had to write it from scratch. Okay. Anytime, so I'm using the word library. I want to make sure everyone knows what I'm talking about. A library basically is all of the code you need to control something in a portable format. So basically, there's a new chip, and I want to be able to use this new chip. Say it's a, in this case, say it's these LED chips that change colors and things, right? Well, someone has gone and written that code for you to make it easy for you to use. So instead of calling 18 different calls to just turn one LED on, they've already written all that code, and now they have a simple little call that says turn on LED, and that's what it does. And you need those libraries unless you want to have to write all of that lower level code yourself. That's what a library is. So if you start doing any sort of code, there will be libraries for almost any chip that you want to support because the open source community has already got you covered. So we do want to talk, there was a good point brought up. Raspberry Pis, super hard to find at this point, all right? Or if you find them, they're super expensive. Now, I will tell you, if you live anywhere within driving distance of a micro center, micro centers are still getting them. You just have to get them when they're in there. So, be checking stock online, because I've seen the stock show up online like it's supposed to, right? So, be checking online because they will restock at Micro Center. I bought 2 Raspberry Pi 4s at a Micro Center not too long ago. All right, so they are still available. You just have to catch them at the right time. Now, I just put this up here. I'm not really going to go through it, but the point being is there are a lot of things shaped like a Raspberry Pi, including Raspberry Pi 3s, Raspberry Pi 4s, and things before that, right, that are this form factor, right, but that have different capabilities. Even a Raspberry 3 to 4 is not the same capability. A 4 is a lot more powerful than a 3 is, right? And if you can't find a Raspberry Pi, there are things called Orange Pis, for example, that you can get pretty readily available. And you can find YouTube channels, you can find websites that will explain to you the difference between an Orange Pi and a Raspberry Pi. Most of the time, it's capability. It may not be as fast, or its graphics ability may not be as good, but you may find out that it does everything you wanted it to do. Okay? So look that up. Orange Pi is one of my favorite alternatives just because they're easy to find, right? They're kind of the secondary one, I would say. But as I was mentioning here, Qualcomm, for example, which is the microprocessor in almost every one of your cell phones, also makes small little boards that are really powerful, but are not nearly as easy to use. And this is kind of where I end up, which is the Jetson. It's a much bigger board. It takes up pretty much the whole space in this arc reactor. Okay, so it's about that big, right? But you really do have a computer on your chest when you're wearing this one. Like I said, this one is a 6-core ARM processor. That means it has 6 CPUs. It has pretty much a middle-of-the-road NVIDIA graphics processor in it. And modern NVIDIA graphics processors aren't just graphics processors. They are multi-purpose processors. You can do image recognition. You can do voice processing. You can do all kinds of things with them because they are general-purpose processors you can write code for now. All right? And on top of that, we get away from SD cards. We get away from USB sticks. And now we have Wi-Fi cards that are built in, which are way more powerful than what you're going to have in your, just your onboard cards. You have actual solid-state hard drives, which you can put on a Jetson, which is what this one's running. 250 gig solid-state hard drive. All right? It's fantastic when you want to record video. Right? You've got high-speed USB on these. And by the way, these, as I mentioned, use a lot of power, run very hot. I have foam on the back of this thing because it heats my chest up when I'm wearing it. So all of this to keep in mind, and like I said, while this is currently powering this monitor and not that, this is what powers that. I wear it on my hip, and it powers that for anywhere from 1 to 2 hours, depending on how much I'm throwing at it. because I can turn things on and off in here. I can turn off object detection. I can record or not record. I can stream or not stream. That all changes the power dynamics of this. All right, this thing I think pulls 15 watts. So I wanted to throw this in there because this is the time we're living in. If you have not been to OpenAI and asked it a question, now's the time. All right, if you want to do any of this, OpenAI is good with code, but not great with code. And as a software developer, I can say that because I use it. I actually use it in my job now. If I have something that I don't want to do, because it's just like something you do all the time, and I'm like, can you just give me a sort function to do this, and here are the inputs, and here are the outputs. OpenAI does a really good job at things like that. In this case, I'm like, can you show me how to code a blinking LED in Arduino? All right, it not only, as you see here down at the bottom, it not only spit out the code, it also told me just in basics how to wire it up. So again, this is really not the replacement for humans. If you know someone that knows how to do this, that's still a better option. But before you bug them for the 18th time, this might be a good place to start. At least you tried. So I do recommend OpenAI. Obviously, you can use it for free. I'm at this point paying for it. But their GPT 3.5 that they have for stuff like this is fantastic. I'm not worried about it stealing my job yet. My first version of Jarvis will probably be plugged into this. I do recommend it. It is a good way to get help. And if it's wrong, which it frequently is, you can give it your error and it'll go, I'm sorry, you're right. So I do that very often. Like, this gave me an error immediately, and it goes, oh, you know what? You're right. I'm like, okay, I know that, but now maybe we can work something out. This is what is inside of here. These are both prototype versions that I took pictures of early in development. As you can see here, there's a display in the front of the helmet. There are lenses in order to have it that close to your eye. You can't see things that are right in front of your face, so you have to put lenses. Remember I told you there was a board in the top. Microcomputers are really good at doing things over and over and over and over again in a predictable manner. Okay? So when it came time to what do I want capturing my sensor data, putting a microcontroller in the helmet made a lot more sense than sending all of those sensors down to this, having it do all of the processing. It would put more load on this computer. So in this case, I'm doing what's called more of a distributed system, which is I have one processor taking care of what it's good at, and then I have the other processor taking care of what it's good at. And you can chain things together all day. And that comes back to what I said, like, do you want to run wires from one computer, or do you want to put a computer everywhere? Right? Because also, then if one computer dies, well, guess what? The other one's still working. Right? Do you want your whole suit to die, or do you want just your left hand to die? Okay? So, and that's how I'm building this one, and I'll show you in a minute. Yeah, if I can get this one. This is a repulsor. If I cut it on, the display will show you that I cut it on wirelessly, because this is all over Wi-Fi. When I cut this on, it's got a Wi-Fi computer in it. It connects over Wi-Fi to the arc reactor. It registers with the suit. So, distributed systems. We're going to do giveaways, and we're going to do Q&A. Do you have any more tickets? And then we'll hand out to anyone that didn't get tickets, and I'll answer questions. Okay, yeah?
Would you end up using more power, like you have the arc reactor. Would you be saving a lot of energy going through that by splitting the processing up, or would you still consuming the same amount?
So, in general, I will tell you that more processors equals more power, right? I mean, obviously, if this one's over here running and it's on, but it's only doing a very little bit of what it's capable of, then I'm overpowering it, right? Now, it's being powered, but keep in mind, that's now on a separate power source, right? So that thing is now running off its own battery, which now I've added more source energy to the system, right? So, like if I had multiple computers but powered to the same battery, then technically I'm using more power than I need to. right? But that's part of the consideration. For example, the helmet is connected to this computer via USB. So this helmet is using the power off of the USB. Okay, so in this case, I'm using probably a little bit more power, but due to the amount of processing that's going on up here, not really worried about it because it's fully utilized. Okay, this is doing regular polling of these sensors, and since it's doing regular polling of those sensors, then that's a lot that's happening there that this one's not having to do.
Actually, you know how you're saying it heats up a lot? So that would keep it from overworking and save, that's what I meant by saving the power. Like, I was mostly talking about heat.
The amount of power that this takes in the top of the helmet versus what this takes is minor. So even if I would have run this to here, like the graphics processing and everything going on here is so high, like from a heat perspective, you won't notice any difference. Yeah, I mean, again, it's levels of, power. If I had a couple of these things doing all the same thing, these don't generate a whole lot of power unless you really overdo it. Yeah.
What kind of 3D printer do you use?
Yeah, I'll be happy to talk about 3D printing too. All right. Thank you for the segue. I did not plan that. So 3D printing, need more info because there are other panels that have talked about 3D printing, so I didn't really want to spend a lot of time in this panel. I didn't want to step on other people's toes that were doing amazing panels, I'm sure. But I knew it would come up and I did want to cover it. So on my YouTube channel, you can find me on pretty much every social media at KrzyFabs because Krzy Fabrications doesn't fit on every social media. So at KrzyFabs on pretty much everything, Instagram, Twitter, YouTube now has at KrzyFabs because they've switched to the ats. So I expect a lot of subscriptions when I get back to my phone. And I knew it would come up, so what do I recommend? So if you're not sure about 3D printing, you're like, I want to start, I want to play with it, because some people are really intimidated by it, and I find that out when I talk to people outside the 3D printing community. But I would recommend, on the left there is what's called an Ender 3. They have been around for a long time, years and years. They have a huge amount of community support, and they are under $150. So if you want to try it and you're not sure you're going to stick with it, or you want to see how it works for your flow of creation, then get an Ender 3. Because even if after using that for 6 months you go, I want something more, that Ender 3 is still sitting there. And you can still use it while you use your new fancy one next to it. Okay, so, what's that? Upgrade, yes. Yeah, they're very moddable printers. So you get one, the first thing you'll start doing is printing upgrades. And you're like, oh, I got a printer to print printer parts. This is fantastic. This is like how most people get started with 3D printing. I know I did that for the first couple of months, just printed upgrades. It was fantastic. Like, oh, this part looks better than this part. Now I need to reprint that first part. But get you an Ender 3. And if you are not a member or whatever they want to call it at Micro Center, and like this is your first time ever signing up for Micro Center, you can get one for $99 at Micro Center. So go get your mom who does not have a Micro Center account and get them to sign up for one, and go get you a $99 Ender 3. One of my favorite printers is the one next to it. It's the Ender 5 Plus. So an Ender, and I'm going to speak in millimeters because that's what we talk about in the 3D printing community. Everything is in metric. The one on the left is 220 millimeters. The one in the middle is 350. So if you want to print a helmet, you're going to be doing it in pieces on the Ender 3. You're going to be doing it in one piece on the Ender 5 Plus. The Ender 5 Plus is my favorite printer. I own 2 of them. A lot of people love them. A lot of people have problems with them. So do your research on anything. Don't just take my word for it. I always tell people that because I don't want you to come to me and screaming at me that your Ender 5 Plus is a piece of junk. So it is a mixed bag. It's a fantastic printer to upgrade. Like you get this, it's one of the more inexpensive large format machines, and then you spend some time upgrading it, and that's a learning process in itself. And then one of my favorite new machines, I just got it, is this Flsun V400. It's what's called a Delta printer. It's a completely different kind of 3D printer. Works the same way, spits out melted plastic, but it uses a different motion system, and it's fast and it is absolutely fantastic. But I think you're going from about $100, $150 to probably about $400. I don't remember how much the Ender 5 Plus at this point. And then the one on the right is probably in the $800, $900 range. Whoa. But you're paying for speed and, again, size there. It's a big printer as well.
So on your YouTube channel, do you go into the 3D modeling aspect of it and kind of show people how you...
I haven't done a lot of modeling. Again, that's not really my expertise. Yeah. I'm a CAD guy. I learned CAD as a kid and then kind of can still do mechanical design and CAD and stuff, yeah. But I don't do a lot of 3D modeling on the channel.
I gotcha.
So I do, if you're curious what I use an app called Fusion 360, which is very popular in the 3D printing community for mechanical design. It's not free, but they have a limited version that you can use as a hobbyist. So if you want to learn some 3D modeling and you don't want to learn CAD, there's something called Tinkercad. Go check Tinkercad out. I taught it to all my kids, and they use it for school projects and stuff. And so it's accessible to everyone as an introductory to CAD design. And the way you use Tinkercad is by, I'm running out of time. The way you use Tinkercad is by taking shapes, and you put shapes together, and you subtract shapes from each other. And so if you can think of the world in geometric shapes, you can use Tinkercad. Like, I want to have a sphere, and I want a hole in the bottom of it. Like, I can do that. That's really easy, yeah.
Okay, quick question. For someone coming from like a C#.NET background, is there a specific language you'd recommend? Like
just go to C. Yeah, go C. I mean, if you already know a C-ish language that uses semicolons to end lines, yes, just go C. So that about does it. That's the point where the camera overheated and I couldn't capture any more of your questions. But again, thank you to everyone who attended. You were a fantastic group of people, and you just made the whole experience wonderful for my first solo panel, and I really couldn't have asked for more. The next thing I need from you is, what other kind of panels would you like to see from me? I love teaching. I love teaching in person, and I would love to give a lot more panels like this. So whether it's give me this panel again, but can you include this information, or can you focus in on this part of this panel and just expand that to a panel of its own? Maybe you want to see a panel on 3D printing or 3D printing cosplay in particular. Leave all of those suggestions down in the comments below so that I know. I plan on attending DragonCon, and I'd love to submit myself for some panels there. I'll be at some RepRap festivals in the future, I hope. And so, depending on what type of convention it is, if I get a chance to speak or present, I love doing teaching engagements like this. So please leave those down below. Again, thank you to everyone who attended. Again, I couldn't have had a better experience. Thank you to MomoCon for accepting me as a panelist, and I hope to be back next year as a panelist, whether I do this one or even a couple of different panels. I would love to do that. I will be at DragonCon in a few months, and I hope to submit myself for some panels there. So that about does it. Again, as always, thank you to my Patreon supporters. You guys are wonderful. You keep this channel going. Thank you to all of you that are sticking around for this kind of change in structure, change in content that I've been doing. And to all of you that just continue to view my videos, that when they see them posted, they click on them, they watch them all the way through. Thank you so much. As always, I'm Chris. This has been Kersey Fabrications, and I will see you in the next video. See you next time.